Okay, so that was essentially what's happening after one excitation pulse. If the y gradient is never turned on and the x gradient is then turned on during data acquisition. So there's a question.
Yeah, about notation stuff. It's a little kind of alpha or what it looks like. There's this.
This prop too. This?
What is this?
This is proportional to. Proportional means equal up to some multiplication. Proportionality constants. It's something one does in school, like in physics. Do you do that? So, so if you have something like this, then this is the same as this, and the proportionality constant is A. Proportional to. So did you never? So that's a typical thing that is done in physics, where you say, I don't know, we did a measurement, and this quantity turns out to be proportional to that, and then you have a proportionality constant, and this proportionality constant is then one of these natural constants in physics, whatever, and that's proportionality. The reason why I put in proportionality here is because I didn't want to deal with this gamma divided by 2 pi, because gamma is the stereomagnetic constant. But in principle, you could also write is equal to gamma divided by 2 pi times this thing.
So that means that the one varies with the other, independent of some multiplication factor.
Yeah. So it means means a linear dependency. So a proportionality and the multiplication constant is not given. Something I actually learned in medicine when I did physics in medicine again. I also learned some useful stuff in medicine. But the main reason is that I didn't want to actually multiply this with some gyromagnetic constant. Or you can also imagine that the gyromagnetic constant is 2 pi that I chose here. Then you have 2 pi divided by 2 pi, and then it's 1, and then it's equal. Yeah, anything else? No. Good. So that was now what's happening if the y gradient is never turned on, and then the x gradient is turned on during signal acquisition. This x gradient is then sometimes also called readout gradient, and the whole thing is called frequency encoding or phase encoding. I think none of these terms are helpful. So they are all over the literature on this, also in the Hüttel book. But to call something readout gradient, that sounds somehow as if the gradient does the readout or something. The thing is, the x gradient is turned on while the data is acquired. And this whole thing about phase and frequency encoding and y doing the phase and x doing the frequency, this doesn't make any sense whatsoever. So just that you heard these terms and can safely ignore them for when you read stuff. The important question is which gradient is turned on when. Yeah. And that the x gradient is called a readout gradient makes some sense because it's turned on during, in this sequence, when the signal is read, so during these 5 signal acquisition times. Good. So that was after one excitation, and now the remaining stuff is relatively straightforward, because now the difference is that there's again an excitation, so excitation here, then the X gradient is still turned on when the data is acquired. So it's off here and then it's on here. Oops. Turn on to something here, which makes the, of course, the magnetic field vary over X space, because this gradient, always keep this in mind, is multiplied with X. Yeah? So that's the slope of the variation of the magnetic field over X. Its time integral, and hence its kx value is still this. Another reason why I have this proportionality there is that I also, when I simulate this, divided this time integral by some constant, because if you would do it up to a scale in this example, then the slope would be much too steep and one couldn't see that and so on. So this is why I just did a proportionality, because the more important thing is that it increases, not how much at this point, because we're not basically doing some quantitative thing. Now the difference is that before the data is acquired, now after a second excitation pulse, a Y gradient is also turned on. And this means that we are now also have, of course, some variation in the temporal integral of the Y gradient waveform, hence our KYT. And of course here the thing is identical, so it increases. And then once the gradient is turned off, this is something that we haven't looked at previously, what happens with the integral? So with the dashed line. So how do I go on here? Do I go further up? Do I go down? Or do I go straight?
Parallel to the x-axis.
Why?
Yeah, because the integral stays the same. It doesn't decrease just because it's turned off, because of these.
Yeah, because the area, also if you're here, if you integrate over this thing, then nothing is contributed here, nothing is contributed here, but this thing is still contributed, so it stays at this constant level. So we have something like this. And then yeah, one can look what's happening, and this is what we do now. So here you now see this case where the Y gradient is turned on to a certain degree. Its temporal integral is here, the dashed line. It then stays on. And then the difference, and the big difference compared to the first thing where the Y gradient was not turned on, is that because there is variation in the magnetic field over the Y dimension, the processing of these magnetic moments vectors over space is faster for higher values of Y and slower for lower values of Y. And hence, if you look at their precession, some point after this has turned on, namely here at this time point 1000, the vectors are out of phase, as you can see here. So here, if they again rotate anti-clockwise, then they are still pointing downwards, while at larger Y values they are already pointing upwards, where at 0 Y values they are parallel. What you also see is that there at time x0 there is no variation over X space yet. So if you look into the X domain, then all of them point in the same direction. So going back to our Fourier basis function view, now we have induced some variation over Y space, and this then looks at this horizontally aligned, or represents this horizontally aligned pattern of the filter function. Now, to increase the spatial frequency of this, one can of course turn on after yet another excitation pulse the y gradient more, then the spatial integral is higher, and correspondingly the ky value is higher. So here it was here it was 0 because there was no time integral whatsoever. Here it was 0.16, which came out from this, and here because the gradient was turned on to double the amount here, it was 0.32. Actually, on a side note, the value of ky and also kx depends on, of course, the height of the gradient and how long it is turned on. So in principle, you can get to 0.32 also by leaving on this amplitude of the y gradient for double the amount of time. Yeah. So that's also sometimes being used in sequence design. So important is the time integral. So yeah, just as a side note, it's not only possible to always increase the gradient amplitude, but it's also possible to basically leave the gradient on for longer. But then, of course, if you leave the gradient on for longer and start with the data acquisition later, then, of course, your whole image acquisition time gets longer. In any case, we now, if you look at this for these 4 time points, so for down this row here, now it's broken. You see that there is this vertically aligned pattern of filters of increasing frequency. Yeah, and then of course this is all at this first data acquisition time point when kx is still 0. But then, of course, also after the second excitation, third excitation, and the fourth excitation, the x gradient is turned on. And now these 2 parameters interact, and you get these essentially oriented filters of different spatial frequency. So here I think it's clearest to see where you see kind of this 45 degree pattern. It's a little bit harder to see maybe at this, but from the Fourier domain perspective, we are now looking at actually the positive case. So we have so we are in the Fourier space. We are actually in this quadrant here. So this was our first row. This is now the second row, and you see this. If you have both positive kx and ky values, you see that they get these different orientations, yeah? Which is what you see here. Now, in terms of the k-space view or the k-space coordinates, we are still acquiring after each excitation 5 values of varying kx amplitude, so 0, 0.13, 0.25, 0.38, and 0.5. But if we start with a higher y gradient, or a non-zero y gradient here, and then increasingly higher y gradients, we are changing the ky coordinate, and hence go to a what is known as a higher line in k-space. So we are acquiring data in k-space at higher y coordinates. And I repeated this thing 4 times. So I simulated 4 excitation pulses with varying y gradients, so that in k-space I cover this upper quadrant where kx is positive between 0 and 0.5 and ky is positive between 0 and 0.5. Maybe if I revise this, I will put these coordinates also up here, that it's a little bit more in line, because here the kx is negative. I don't know why I did it exactly like this. I have no idea. That the match between the quadrants of k-space between this figure and the other figure is a little bit better. The data that is acquired is still the summation over all of space at each time point of the product of the complex exponential term, so this two-dimensional entity, and the magnetization vector, so this two-dimensional entity, summed over all of space, which gives you a two-dimensional number, a complex number. And this, I didn't say earlier, this is of course the absolute value of these numbers, because these MR signals are always complex, so you always have the real and the imaginary value, and this is just the absolute value, so the square root of the real and the imaginary part, if you remember complex numbers. Yeah, so this is then essentially the k-space raw data that is acquired by such a sequence. Yeah, well, there are two, or at least one thing that is important, so that you don't get confused with respect to echoplanar imaging. Here we assumed, or I assumed, 4 excitation pulses. So there was excitation here, there was excitation here, excitation here, and excitation here. In real echoplanar imaging, this whole thing is done with 1 excitation pulse, because you can also see here that in this example, this takes 2 seconds, this takes 2 seconds, and this takes 2 seconds, and all for different lines in k-space, so this would take quite a long time. So one specific thing about echoplanar imaging is that it's quite fast. Essentially, it uses 1 excitation pulse, and then it uses in between these acquisitions of k-space, it doesn't use a new excitation pulse, but it just gives a very brief what's called blip of y gradient, which moves to a next line in k-space. And then there are all sorts of variations of how to fill in k-space. So that's where then sequence design really starts. So for example, because I wanted to have things quite simple, I started with the X gradient at the first image acquisition time. Another way that is often used is what is then also called gradient echo imaging, is that you put up a Y gradient negative up first, so that you get some out of phase synchronization prior to image acquisition, and then at one point things getting into phase again, namely when these things are equal, so that you get the strongest value at this time point, which is then called echo time. So this goes into gradient echo sequences. But I wanted to start even simpler, so that at one point there's also no desynchronization or dephasing whatsoever. So I used this very basic 2D Fourier transform simulation. Okay, so this is then, why I'm saying this is that if you use this, then you could also, then you would fill k-space differently. Then you would, for example, start with negative kx values, so start here and then go to the other half. And then, sequence design is essentially about how you fill k-space. So maybe then going up here, or there are other ways where you, I don't know, there are all different ways to go through k-space. The important thing is that, of course, k-space in the end determines how your image looks. Because as you remember from discrete Fourier transform, the number of data points that you acquire in k-space determines the spatial resolution of your image. So essentially, if you only acquire data in the center of k-space at low spatial frequency, then of course you only have a low spatial frequency in the in your image. If you acquire many, so the number of points that you acquire in k-space directly maps to the number of image points you get, namely voxels. And so k-space determines your image quality. So what I did here, and maybe this is then to finish this bit, what these what these things refer to is this upper quadrant of K-space. Now, these are 5 times 4 values, and they are these values that are plotted in this upper quadrant here. Now, if you look at the spatial frequency properties of this, you see that there is some redundancy, right? So kx minus 2 and ky minus 2 is the same as kx2 and ky2. Yeah, it's the same spatial frequency filter. Yeah, and the same for this and for this. So what I did, because also the simulation takes some time to plot the arrows and so on, and also to still be able to see things and not have like 16 times 4 of these pictures, I reproduced the data that is acquired here by this pointwise multiplication and summation over this. I reproduced this in reverse order, so according to the ordering in K-space there, and there. So basically these parts of K-space on my simulation here, so a little bit small, they are reproductions of the of this upper half, because acquired data I only have from this here. The reason why I did this is because I wanted to have more data points in K-space to then use the inverse 2D Fourier transform to recreate the image. So I have these data points for these K-space coordinates. They are shown here, or the absolute values are shown here, and then I use 2D inverse Fourier transform to now map this into image space, so the entire K-space here, which is then shown here. So that's the discrete, so that's what we called an image last time, where now we have as coordinate voxels, which are of course related to the K-space points that we acquired. And you see that more or less the actual image that we have here, namely the central disk here and everywhere else, is reproduced. It's not awesome, as you can see. It actually looks like there's some aliasing, so if you have a lot of imagination, like I do, for these kind of things, then you see then almost there. Come on, load it. '21st century. Then you see that there seems to be double images, or a little bit of ghosting, if you want. So there seems to be a disk visible here in the middle, but maybe if I had the 25,000 euros that Alt wants to give to me because I digitalized things, it would be faster. Anyway, he said there's this, that to make something like this digitally available costs 25,000 euros. Oh. So you see there's maybe, it looks a little bit as if there's a ghost artifact up there and also down here. And this, of course, has to do with the fact how you sample, with which spatial frequency filters you sample an image which has certain image properties. So remember that we discussed something like Nyquist theorem, that you should make sure that you sample at least twice the highest frequency that you're interested in, and of course all these considerations also come in here. And I really did not optimize any of this in the simulation that I ran. So there is definitely, and this is now, if you really want to understand more about magnetic resonance imaging, There is, of course, based on this, there's the opportunity to do a master thesis and to continue with this simulation, so the simulated MR scanner, and optimize this for imaging different images that you can create here, and also implement different sequences. So, for example, a gradient echo sequence, as I shown here, or an EPI sequence that is not shown here, where you have only one excitation pulse. So that's actually, if you want to spend a year working on this, then you definitely know MRI, and this gets further. If you feel like you want to do some social neuroscience and have people touch each other and then go into the scanner, that's also up to you. But yeah, so there is, actually I think I learned quite a lot from doing this simulation, which is good. Yeah, so in principle there is now MATLAB code that does a 2D Fourier transform by simulating the physical model that's behind MRI. Yeah, I think at the code, it's not really worthwhile looking at the code now, but you have the code, so you can look at things in there in more detail. And I think I'm then done with that. Let me have a look whether I want to explain something else. No. So this whole thing is fairly much inspired by this figure in Nishimura, so figure 5.7, which I think is quite useful. It goes a little bit beyond that because it also does the discrete Fourier transform. Yeah, I think from my perspective, that's essentially it. So see this again as the integrated view of everything that we've discussed so far in this part of the course. So you have this rotation of the magnetization vector, you have the gradient waveforms, you have K-space being filled, and you have the 2D Fourier transform aspects. What we didn't discuss at all, and which will remain a mystery for you guys unless you at one point start looking into that, is how the excitation actually works, because we didn't discuss that at all. So the excitation, a brief story about the excitation is that you know that the static magnetic field induces some rotation of the magnetic moments in space, so it makes them align. And now if you give a variation of a magnetic field, then you can also use this effect to rotate them wherever you want. And this is actually how the excitation works, but this requires a lot of coordinate system back and forth, so takes some time, so I didn't do that at all. But at least I think what has been achieved is that we link this basic precession thing, Bloch equation, to the image formation process that happens via two-dimensional Fourier transforms. And that was an important goal. So I'm done with that now. Questions right now?
Yeah, I have a maybe simple question, but I just kind of trying to get the entire picture. So what we discussed today is like the process that goes step by step from going from this transform values here to voxel. From the what? To voxel. To voxel. Yeah. So in the end we are at voxel. So this is like step by step scene. And also I just got a bit confused. Could you repeat like once and forever? When we turn like X gradient, when we turn like a Y gradient, like.
Now, once and forever, that doesn't quite work because you have, it depends on the sequence that you use. Yeah. Okay. So so whenever you hear somebody, okay, we need a sequence for our experiment, what the sequence actually is a protocol or program that says when Z gradients are turned on, when excitation pulses are sent, when X gradients are turned on, when Y gradients are turned on and off, both of them, and when the data is acquired. So that's what a sequence is. And of course, there are different variations of sequences. So you can...
What do they depend on?
No, what you want to image and how you want to image things and how you want to fill K-space. Well, yes. The example that we discuss here is exactly this here, where we assume we do an excitation. Well, maybe let's go to the bigger one that I draw myself. That's this one or this one. Here, this is one example where we first assume that we fill each line of K-space, so in the Y direction, using a different excitation. So we give one excitation pulse, and then we turn on the the Y gradient after sometime after the excitation, and then we turn it off. And during signal acquisition, we turn on the X gradient. Behind that, we already had turned on the Z gradient, and by means of excitation and tuning the excitation to a specific lambda frequency, selected the Z coordinate. So that's one example. The problem, or one of the things with this example here, is that to have these points in K-space that we looked at, we always need a new excitation. And then you can say, okay, can't we do this faster by just having one excitation and somehow doing this quicker with stronger gradients or whatsoever? And all these considerations, or the gradient echo sequence that I briefly mentioned, they go into sequence design, and essentially by deciding on when and how much you turn on gradients and you use excitations, you get control over what kind of data in Fourier space you acquire and how this then translates to the image that you get. So the thing is, so in this sense there is no once and for all, because also this day somebody somewhere develops a new sequence, because that's what people do. It's what the job of MR people is, to tune the image acquisition to certain things. Yeah. But in this case, for this example, once and for all, the Z gradient was turned on during excitation. We don't talk about it, we don't see it. The excitation is given 4 times. The Y gradient is turned on to different amplitudes in this time window, and the X gradient is turned on during signal acquisition at this time. Yeah? Other questions? No. Good. So yeah, then maybe next week you have questions regarding the MR business, then we can discuss them. Otherwise, the magnetic resonance imaging lecture bit is over now. And also the whole neurocognitive methods winter term is over now. Because next week we'll start with, essentially in the summertime, with me telling you how the programming seminar will work, which will be different than this. Yeah, good. Then let's have a break and continue at 10 with statistical methods.